And then I'm gonna share my iPad screen. All right, y'all can you all see this? Like just a blank white screen? Cool.
Yeah.
All right. All right, let's get started. So today's going to be a pretty fun day. This is going to be a whole crash course on trees, pretty much. So if you've been following Leetcode Friday, we've already gone over arrays, linked lists, stats a little bit. We've done 2-pointers, we've done sliding window algorithms, and now we did binary search. So moving on from binary search, we're going to actually start with something called trees. So if you've taken 313, then you probably have a general idea of what these are. If you haven't taken 313 yet, well, this is perfect because you're going to learn what trees are. All right, so just to start, this is a tree. It's very pretty. It can have apples and stuff. I don't know if you guys like apple picking, but just kidding. This is not what trees are. All right, so trees are a abstract data structure that we can use that have a really interesting property. They have a left and a right pointer, and you can use them to really make things a lot more efficient. So just to show you an idea, this is going to be a node, and it has a left and a right pointer, and it has children. So this is an example of a very basic tree. We have 2. This is actually called the root. The first node that you see is a root. And then this is called a leaf, like a tree. But it's kind of upside down. So if you really think about it, this is the tree, right? And you got the little green stuff. Here's the root somewhere around here. You got some branches, right? Left and right branch, sort of going around. And you got the leaves, which are at the end of the tree. So that's where the idea of a tree comes from. So we're going to build up on this. All right, I'm going to scroll up a bit. And here we have a little tree. And I put a little green to show you the leaves, but here's an example of a tree. So let's see what's going on over here. This is a tree. It's actually called a binary search tree. A binary search tree, or a binary tree in general, has the property of having each node has 2 children, at most. So it's going to be the root or parent node and 2 children. Okay, so binary means 2. There are things like, I think, ternary trees where you can have 3 kids, or n-ary where you can have like multiple kids, 4 children, whatever. But binary trees are usually pretty common. That's what we're going to first play around with. So a binary search tree is a different type of binary tree that has this very specific property of being sorted a specific way. So when we have a node, okay, this is a node. Let's say it's 10. All nodes to the left of this node, of this tree, are going to be less than 10. And all children of these are going to be less than 10. If your mic is on, turn that off. And then anything to the right of the 10 is going to be greater than 10. Okay, so everything is going to be greater than 10 forever. And we can use this property to really be able to move to kind of sort things and search things in a very efficient way. So here we have a binary search tree. Let's go through it step by step. All right, so here we have a root. It's 4. Okay, so at our root, we have 2 children, the left child and the right child. The left child is always going to be less than the root. The right child is always going to be more than the root, which makes sense. In terms, this is as in like, it makes sense that this is how it is. So here we have 4 going to 3, 4 going to 6 on the right. Okay? And then, at this 3, we have another junction, where here actually is pointing to null. The right child is nothing, but the left child is actually less than 3, it's 2. Okay? And then 2 has 2 children, null and null. There's nothing there, so it stops over there. Let's look at the right side. The 4, 6 is bigger, so we're going to put that there. Okay? And then here we have another tree, subtree. 6 to the left is smaller, so we have 5, and 7's bigger, so we have it to the right. Okay, so this is the basic property of a binary search tree. And the really cool thing about having trees like that are this way is that we can actually search for them really, really fast. So let's try. So our first question that we had in Leetcode, I'm not going to pull up right now because it's pretty simple, and we can just go through it in this picture. So our first question that we had was called search in a binary tree, a binary search tree. So this is our binary search tree, and say we want to find the number 5. So, or actually, yeah, say we want to find 5. Okay. How would we do this algorithmically? Does anyone have any idea how we would start? Anyone? I can't read chat, by the way, so you'd have to call out loud. Have anyone idea how can we start searching for 5 if we're starting at the root? We have the root. We're given a root. We want to find 5.
We would check on the values greater than 4. Or
Yep.
Root, sorry.
So say our target is 5. Is 5. Okay. So we know that the property of a binary search tree is that anything greater than our root is on the right side, anything less so over here, anything less than the root is on the left side. So we can kind of think of it like this, right? If target is greater than root, right? Search, I can't spell search apparently, search the right side. Else, search left side. This is a general idea of trying to find something in the binary search tree. We can compare with the root, right? So we have 4, and we're looking for 5. So let's try that. Let's go through this tree ourselves. So we're at 4. We're looking for 5. Is 5 greater than or less than 4? It's greater than, right? So we're going to move down here. Cool. Now we're at 6. Is 5 greater than or less than 6? It's less than 6. So we're going to move to the left. And we found 5. So cool. It exists. All right, let's try a different example. So say we want to find let's find 1. Okay? So we're starting again. We're here. Right? 4, 1 is less than 4. So we're going to go here because we're going to move to the left. Search the left side. All right, now we're at 3. This is the new root. Is 1 less than 3 or greater than 3? It's less than. So let's search the left side of this tree. Okay, let's pretend this is null. So search the left side. Okay, now we're at 2. Is 1 less than or greater than 2? It's less than, so let's search the left half of the tree, which would leave us to null. And since it's not there, the number doesn't exist. All right, so that's kind of how we search in a binary search tree, specifically a binary search tree. This binary search tree you would consider fairly balanced, but what if we had a binary search tree that was something like this? Ready? Move this up a bit. All right. So say we have a binary search tree like this. How long would it take us in terms of big O, right? To get to 7. Worst case scenario. Does anyone know?
Log of n?
Well, right now, in this specific binary search tree, that's not balanced. It would take, we have n items, and you would have to traverse n times. So there's actually something you guys should make sure to know is the binary tree balanced? There are versions of binary trees that are balanced automatically. I think they're AVL trees, but or some I forgot the specific name. But binary search trees, this is a valid binary search tree, right? Because everything to the right is bigger. This is valid. This is okay. But this is practically a linked list with extra pointers for no reason. So worst case scenario for search would be O of n. But let's move back now. We say we have a balanced binary search tree, and it's actually pretty good. Here, we have this concept of we're dividing and conquering the search. So every time we're looking at the root, we are cutting off. Say we're looking for 7, right? We are optimally cutting off half of the tree, because we're only going to search this right side of the tree, and we're not going to search the left side of the tree anymore. So we cut off half the problem. So now we're at 4, searching for 5, right? We cut off half of the problem. We're here, searching till 5 is less than 6, so we cut off the other half of the problem. So cutting off half of a problem in general is actually something that we call log of n. So searching in a binary search tree that is balanced would be actually big O of log of n. This is super efficient. So this is a lot better than linear search through an array, or especially if you have a linked list, which is where this is practically is a linked list, where we talked about a couple weeks ago. It's searching a linked list is big O of n, because there's no really way of dividing and conquering a linked list. You have to go pointer by pointer. So binary search trees are beneficial because you can do them in log of n, which is really, really handy. All right, so now let's code that up. Let me go back to my Mac. Okay. So now you're going to be amazed. Binary trees are super recursive, so I'm going to give you a very, very easy solution. All right. So let's start off with just the base case. If not root, so if the root doesn't exist, so if the root is null, or value is equal to the root.value, because right, we're looking for a number. We're given a root of a binary tree and an integer val. We're trying to find the node that has the val, or if it doesn't exist, return null. So that's our base case. If there is no root or value, return null, aka just return root. Okay, and then we're gonna just do this. Return self. So self is just object-oriented stuff with Python. Search binary search tree. Root.value. Root.left, comma value. If value is less than root.value, or else self.search binary search tree root.right, comma value. So let me quickly just make sure I wrote this correctly. Hold on, what did I do wrong? Oh, wait, the rule? Oopsie, I can't spell. There you go. So we did it. So all we did was what I said out loud, right? First, base case. Once we get to the end of our search, either it's going to be null because we got to an empty pointer and it doesn't exist, or we actually found a number. We're going to return that root, that specific node of the binary search tree. Or else, so that's our base case. And then we're going to do the recursive case. We're going to search the left half if the value is less than the value that we're looking for, or else we're going to search the right half if the root is larger than the value we're looking for. And that's all we're doing. So we're just calling this, and it's going to recursively answer itself, and it's literally 4 lines of code. We submit it, and we're done. Any questions on binary search tree searching? This would be O of log n.
Just a question about the Python. With your, I've never done Leetcode with Python, so I don't know why. But on root.left and root.right, why is it underlined?
Argument of it's just some weird Leetcode thing. I don't know. It's just
Yeah,
saying,
just Leetcode bugging.
yeah. Don't worry about it. It works and it's accepted. So that is our recursive solution. But
Could you do
Someone
that
else have a
outside?
question?
Yeah, I also had
Sorry?
a question. Could you do that in C++ and not Python?
probably could. I don't have the solution. I never did this in C++, but I'm pretty sure you can do the same thing. I just don't have it off the top of my head, so I have to remember the syntax. But it's the same thing. You can just probably say like if what's a root, or I guess that value.
I
It's
think that would
root.
involve pointers.
No,
The null pointer? Yeah,
Something
no,
like
not
this.
null pointer.
yeah, if something like this, or what's it? I haven't done C++ in
Yeah, yeah.
forever. Something
I
like
got
this.
it.
Yeah, I haven't touched C++ in like a year. All right.
That's okay.
So then, you're welcome. All right, so this is the recursive solution, and just for fun, I'm going to show you the iterative solution. So this is going to be same O log of n, but we're going to go through it iteratively, just for fun. So whenever we're doing iterative solutions for searching or anything with pointers, like linked list or trees, you want to have a current pointer. So current equals root. That's going to be our sort of like our pointer saying where we're at specifically. And then we're just going to say while current. So while current pointer exists, so while the node exists, if the value is equal to to the current value, just return this current pointer. Else, if the value is greater than current value, the current is equal to current dot right. So what we're doing now is that, so say we're at the 4 in that picture of our linked list. That's an example 1, right? Say we're looking for 7, and we're at 4 right now. Or actually, let me add the next line. I'll explain it better. So an else current is equal to current dot left, and then return none if nothing happens. All right, here we go. So say we're looking for 3 on this link on this tree on the left, right? We're gonna have our current pointer at 4, and then we're gonna compare. All right, is the value we're looking for 3? Is 3 greater than or less than 4? It's less than, right? So we're going to do the else statement. Current is equal to current dot left. So the 4, now we're at 2. So we're at the 2 subtree. We're gonna do it again. 3 is greater than 2, so we're going to go to the right. Current's the right. Now we're at 3. Perfect. Is the value current equal to the current value? Yes, it is. It's 3. It's 3, so we're returning the 3. That's all we're doing. And that's the iterative solution for binary search trees. And there you go. All right. Now moving on. We're gonna be speeding through this one. So now we understand what binary search trees are. How do we add stuff to it? So say we want to add a node to this binary search tree. Let me just erase everything else. To add a node in a binary search tree, where do you guys think would be the most optimal place to place a node? Say I want to add, let's say we want to add let's do 1. Where should we add 1? What would be a good place to add it? Does anyone know?
Would it be the left of 2?
Yeah, we want it left of 2, so we would want to add 1. Actually, so the what you actually want to say is you want to add it to the leaf node. We're going to use one of those null pointers and add that instead. So we're going to turn, whenever we insert something, we insert it to a leaf. So here we added 1. Let's say we want to add 8. Okay, we want to add it, hopefully, I would assume around here, because it fulfills the binary search tree properties. 6, 7, 8, 7, 8 is bigger than 7. So we always want to add things to the leaf node. All right, in binary search trees, always add to leaf nodes. And it's sort of the same process to get there. What we're going to be doing is, this is sort of a recursive idea. So we're going to start from the beginning, from the root. Okay, let's delete. I'll leave this here. All right, so we're going to add 1 first. Okay, so is the value 4 1 less than or greater than 4? It's less than. Okay, so let's insert it to the left side of the tree. So now we're going to cut off half the problem. We're inserting to the left half. This is recursive. Okay, now we're at 3. 3 is still greater than 1, so let's insert 1 to the left half of the tree. Cut it off again. All right, now we're at 2. We're at, is 1 less than 2? Yes, it is. So we're going to insert it at the left half of the tree. Okay, and now we are hitting a base case because we hit null. So if it is null, if the current pointer that we're looking at, right, is null, we want to return a new node, a new tree node with the value 1. So then recursively, it's going to return 1 here. It's going to return 1 here. Actually, let me use a different color. Recursively, it's going to return 1 here, here, and back here. And now we have a new tree that has 1 in it. Let's do the same thing on the right side. We want to add 8. All right, 8 is greater than 4. So let's insert 8 to the to the right half of this tree. So we cut off this whole problem. Now we're at 6. 8 is bigger than 6. So insert it to the right half. Cool. We're at 7. 8 is greater than 7. Insert it to the right half. Hit a base case. 8 is null. This is null. So we're going to return a new tree node with the value 8. And it's going to bubble back up over here. Okay? And that is basically insertion for a binary search tree. Does anyone have any questions before we code it out?
Yes, I have a question. What do you mean by bubble backup?
So recursion, the way it works, it's been a little while since we did 111, but pretty much what you're doing is you're returning a whole tree. So recursively, you're going all the way to the end and you're returning this node. So then this is going to become, so remember, we're inserting stuff. So we're going to say root.left, for example, is equal to insert whatever stuff, right? So our say this is 2 is the root, the left is going to be insert the node. So this is going to be returned. So this is going to make it root.left. But it'll make more sense in the code. You'll see it. But it's going to be returning something, which is why it's kind of bubbling up, and now we're returning everything back up there. It'll make a little bit more sense when you see the code. So let's go to the code real quick. All right. So it'll make a little bit more sense when we coded that. So here's insert. Let me just quickly pull it up. All right. So if not root, this is our base case. Return tree node dot value. So over here on the top, this is talking about the definition for a binary tree node, right? We have a tree node, that's a class. The self dot value is the value. Then we have a left and a right pointer. So once we get to a null pointer, we're going to return a new tree node. So it's new with the value in there. Okay, that's our base case. Now, if the value is greater than the root dot value, then that means that we should insert it to the right side. So root dot right is equal to self dot insert into BST root dot right value. So what we're doing here is if the value, say we're at over here in this picture of, I guess, 5, 1, 2, 5, whatever it is. So say we want to insert something after at 4 on the second picture, right? Or say we want to insert 7, right? Yeah. 8 in this picture. Then it would be insert to the right. Sorry. Pretty much it's like search. Else root dot left is equal to self dot insert into binary search tree root dot left value. So pretty much we're just doing the comparison, right? We're cutting the problem in half. If the thing we're supposed to insert is larger than our current root, insert it to the right side. If it's smaller than the current root, insert it to the left side. Once we hit a null pointer, return the new value in the tree node. And we run that. Wait, wrong answer. What did I do wrong? Oh, whoops, I forgot to return the root. Yeah. There we go. So there we go. I don't know why the runtime is so slow. Again, don't worry about Python runtimes. It gets very, very weird. But this is technically big O of log n to insert. Because we're dividing and conquering. We're breaking the problem in half. So on average, it's going to be log n if it's a balanced binary search tree. And yeah. Any questions on insertion? No questions? All right. Then we're going to delete stuff. So this is all pretty much a crash course on stuff that you learn in 313, but honestly, that class is kind of, at least the one I took, was very theoretical. And at least in my case, all my professor did was read the textbook, so it wasn't really that helpful. So hopefully this is helping you guys understand trees a little bit better. All right. So now we want to remove from this binary search tree. Say we want to remove, let me delete my added stuff. Say you want to remove something. We have 3 different cases that we're going to have. Okay, so case 1 is that the target node has 1 child or no children. So say we want to erase 7. We want to delete 7. Okay? This is going to be the easiest one to do. We want to remove 7. So all we have to do is just remove it. We just turn this 6 pointer to null rather than 7. Easy peasy lemon squeezy. That's the easiest base case. You're just turning it to null. Okay. Now let's pretend it has 1 child. Okay. Then we want to remove 3. This is a little bit more tricky. We have to now have instead of just saying this goes bye-bye, what happens to 2? Right? It's going to disappear. If you just delete 3, 2 is gone as well. We don't want that. So what we want to do is actually 0.4 to 2. And that kind of will that'll fix the whole binary search tree, because then this will just become 2. That's case 2. So having one child. Any questions on case 1, which is no children in case 2? Sorry, case 1 and case 2 so far? Pretty much no children, just delete it. One child, move the pointer. No? Okay. So then here's the harder one. The case 2 is where the target node has 2 children. Okay, so let's actually do it with something really hard. Let's say we want to delete 4. Right? 4 has 2 children, it has 3 and 6. What happens if we delete 4 and we just say bye-bye? The whole binary tree is gone. This is all gone. This is deleted. Everything is dead. Life is over. Don't do that. So what can we do to replace this 4? We want to still have a binary tree. What number would you guys think would be the best number to replace this 4 with?
5.
5. Cool. So if we replace this 4 with a 5, is this still a binary search tree? Yes, it is. Because the left is still smaller and the right is still bigger. So yeah, that's the solution. Pretty much when you want to delete a node that has 2 children, you want to replace it with a leaf node. So which specific leaf node? So say we have, okay, so you either want to replace the leaf node you either want to replace this number with the smallest number on the right side of the tree or the largest number on the left side of the tree. So if we replace this with the largest number, which is 3, this would still be a binary search tree. This would be 3. That works. Or you can, but there's not really a child node, so this would cause a little bit more issues. So I would probably not do this personally, but you can, in this case, replace it with the smallest leaf node of this binary tree of the right side, because that'll still fulfill the property of binary search tree by making it a 5. So you're replacing these 2. And then just by replacing the value, you don't have to swap the tree node itself. You can just say the value itself is 5. And that way you don't have to mess with pointers. That's all you have to do. All right. So again, this will make a little bit more sense in the code, but that's sort of the concept. So again, just to reiterate what we're doing, if we want to delete a node and it has no kids or 1 kid, just delete it. Bye-bye. No problem. Easy peasy. If it has a child, right, 1 child over here, then you don't want to delete it because it'll kill the children as well. So we move the pointer over here. And if it has 2 children, then you want to find the min or max of each of one of the 2 sides. So say, let's just for arbitrary reasons choose the right side. We want to find the min of the right side. This will be here, and just make this 5, and we're good to go. All right, let's do this. So this is actually considered Leetcode medium because it is a lot harder. The other ones were like 2 lines of code or a couple lines. See, like inserting is just adding a leaf, searching is just, well, this is a little longer if it's iterative, but the recursive is like 4 lines. All right, so if we want to delete a node, let's start with the base case. Okay, so in our tree, right, we always want to go if not root. So if node is not in tree, not rot. If trees are rotting, they're going to fall and break. All right, if not root, return none. So what we're doing is we're saying that, say we want to delete a number, right? And say we have a binary search tree and it's between 1 and 10 and it's saying to delete 25. That's not going to exist. So we can't delete anything. So just return none. That's one of our base cases. All right, if key is greater than root.value. So again, we're comparing left and right. We're dividing, conquering. Root.right is equal to self.delete node. Root.right key. So all we're doing is we're calling this function back to itself. If the key is greater than the root, search the right half and delete the right half. Else, if key is less than the root.value, delete the node from the left half. So again, it's just recursive, right? Key bigger, do right half. Key smaller, do left half. Same thing as before for inserting, search, everything else. Here's our else case. If not, root.right. So here is if we have one child. Return root.left. Else if not root.left, return root.right. So all we're doing here is this is the case of if we have one child. So say we're deleting a number. Let's see if we can find one. Yeah, say in the second one we're trying to delete a 2 from the 4, 2, 5, 6, 7 tree, right? It has one child. So if there's no root.left, right, then return root.right. So we're saying that we're going to just return 4 back to 5. Because again, over here, we're setting root.left or root.right equal to the whole tree that's being recursively built from the bottom up. All right, so here we go. And now we're gonna have a second else. So again, the first one is just we're getting down to the bottom of it. We're trying to find it. Once we found it, if there's one child, we're gonna do some magic to try to recursive magic to create the new binary tree. And then this is for if we have this else case is going to be for if we have 2 children. So if not root right, if not root left is for one child, and here's for 2 childs. We're gonna find a min node, and then let's actually do a extra method to make this easier. So here's def def min node value, min val node self root. Let's make a little easy helper function to find a min node. We're going to do iterative current equals root. And all we're going to do is while the current pointer exists and current.left exists, current is equal to current.left, and then return current. So what we're doing here is we're going to go to the right side of the tree, and we're going to just find the minimum node. So we're just going to go all the way down left into the tree because we know that everything on the left is smaller. So we're just going to go all the way down to the left until we get to the end. That's all we're doing. So we're going to find the minimum node, which is the thing we're going to swap it with. Self.min value node. We're going to run that on the right side of the tree because we want to find the minimum value of the right side to swap it with. And then root.value is equal to min node.value. So we're swapping the values. And then root.right is equal to self.delete node root.right min node value. So all we're doing here is now we're deleting the original node. So say if we were trying to replace 5 in this tree, right? Say we want to try 5, and say we did it on the left side. So, well, it doesn't really make sense because I'm trying to find a better tree. But yeah, let me go back to the iPad. So in this tree, so we want to delete this 4, right? So all we're doing is at this point, the min node is 5, right? We searched through. So we're over here. We found the min node. It's 5. So we swapped 4 with 5, and now we have to delete 5. So then we're going here and saying bye to 5. That's what we're doing. Okay. And then we are going to return root. There we go, and it worked. First time. So this is also going to be big O of log of n, right? Because we're dividing and conquering. But this is a bit of a pain to kind of code up. I recommend this is one of the stuff you should probably memorize. Is just learning how to search, insert, and delete. If you do know it conceptually, coding it's a little bit annoying, but once you kind of get the concept, hopefully it makes a little bit more sense. Does anyone have any questions on deleting nodes? I know this one's like a little bit of a difficult one. Any questions at all?
I guess for my implementation, I kind of converted your code to Java. But for some reason, it does not work. Do you want to take a look at it real quick?
I can try.
Here, let's hold on.
Actually, can you yeah, just send it into the
Yeah,
into
let
the
me I'm pretty sure it's the same, but let's see. Are you able to see the chat?
Which chat? Are you? Oh yeah, I see you posting it now. Oh lord,
That's Java.
you're making me do Java. What does it do? It works sometimes. Oh, it's not actually delete. So, let's see. Maybe, because I don't, and I'm sure this is probably some like Java syntax stuff. Don't you have to do
Yeah.
something like tree node min equals new tree node or something like that?
Nah, you don't have to.
I don't know. You probably must have done something wrong with the Java just in general.
What did you return in min node? You returned cur, right? In
Oh,
your
cur value.
Python? Oh, cur.value, gotcha. That's why.
Oh no.
No, you have to
Cur.
convert it to you have to convert it to an integer. So public it should be public int.
Yeah, you know what? You do this yourself.
Yeah.
I like Java. All right. This is why we use Python, guys, because Python is so much easier. We don't have to worry about all of this type stuff and all this curly braces. We just use English and we do our stuff. All right. Let's move back to the better language. All right, so now we have officially solved all of the search, insert, binary, delete stuff. This are very fundamental algorithms that you should definitely memorize, or at least understand the conceptual level. You should be able to draw out a binary search tree. You should be able to insert it and explain how to insert it. You should be able to know how to delete. So if you're in a tech interview and they're saying, how do we delete something from a binary search tree, you should be able to tell them the three cases, right? If there's no children, just delete the node. If there is at least one child, then just return the right or left side, and that'll delete that child. If there's two children, you find the min of the right side or the max of the left side. You should be able to explain that. I will send this code so you can kind of analyze it and just study it. I recommend you go like line by line, draw out the binary tree, and really just go through this algorithm and try to understand exactly what it does, because this is definitely a little bit more confusing. So I don't blame you if you might feel a little confused. But draw out the binary tree one by one, go line by line, and just try to analyze it, because this is a very important algorithm. All right, moving on. So now this is going to be a quick one. So we're gonna do depth first search and breadth first search. There's 4 questions for this, but it's practically the same exact question. Just you're moving one line of code around, so it's not really anything. It's not really a big deal. So what we're going to be doing now is just quickly going over search. So we talked about binary search tree search, right? Which is where binary search trees have a very unique property of the left being smaller, the right being bigger. But there are other binary trees. You can have a binary tree that's like this. 2, 1, 0, and it can be like totally random, right? That's totally fine. You can have a binary search tree like this, or a binary tree, sorry. This will not be a binary search tree because it doesn't have that property of being smaller and the right being bigger, but this is a binary tree. So we still need to be able to know how to search through these things. And for that, we have things called depth first search and breadth first search. And through depth first search, we have 3 different versions of that, which is Inorder traversal, Postorder traversal, and Preorder traversal. So let's start with the easiest one, or at least the one that makes the most sense conceptually. So we're going to use the same tree just because we've been using it this whole time, so we can so it's not really anything new or crazy. But let's pretend that we don't know that this is a binary search tree. This is just a random tree that we're given. No knowledge. It's just a tree. So we cannot run binary search tree search, which would be log of n. Okay, we can't do that because we don't know that's a binary search tree. So we can do it 2 different ways. We can either do depth first search, where we kind of go all the way deep inside one side, and then go all the way deep in here and all the way deep in here. Or we could do breadth first, which is we're going to check level 1, check level 2, we're going to search level 3, and go level by level. So those are the 2 specific versions that we're going to go over today. So again, breadth first search, sort of like levels, level by level. And then depth first search, DFS, is go as far as possible until you hit null. Right? So let me erase this to make it a different color. So breadth first search and then depth first search. Right, would be something like here, hit null, then go all the way back here and here. Okay? So let's do it. Let's start with depth first search because it's a lot easier to understand. Breadth first search can be a little bit more difficult. So for depth first search, we have 3 different versions. We have, let me erase all of this. Let's start with Inorder. So we have Inorder. Ready? So the order we visit these nodes is sort of the way that you would probably read this out loud to yourself. It's the best way that we described from in our 220 class. So what we would do is we'd start here, okay? We're gonna start at the root, and we're gonna go all the way down to the last leaf. And that's gonna be our first node that we visit, technically, that we return. Okay? This is the first node that we look at. Then we can't go any deeper. There's nothing here. So let's go back up here. We bubble back up here, and this is our second thing we're gonna look at. Then we're gonna hit the root. So it's gonna be 1, 2, 3, right? And then now we've done the left half. Let's do the right half. So then we're gonna go all the way deep as far as we can, and we hit 5. This is the furthest we've gone because we hit null, so we can't go any further. So that's gonna be our 4th node. 4, and then we're gonna go back up, and again we're here 5. This is the new root, and then we're gonna search all the way down the right, and it's 6. So this is the order that we would look at for Inorder. I'm gonna erase all the lines. I'll keep the numbers there so you can kind of compare and contrast. Oopsie, let me go back to 1. Okay, this is Inorder traversal. Let's do preorder. So here's preorder traversal. We're going to start here, and it's going to be our first node. And then we're going to go down here. It's going to be our second node. We're going to go down here. It's a third node. Then we've reached the base case. There's nothing here, so we're going to go to the right side of this tree. So now we go here. It's our 4th node. And then we go to the left. It's our 5th node. And then we go to the right. And it's our 6th node. Okay? So this is going to be preorder. So if you're you should probably start to see a pattern. I'll explain the pattern a little bit better once we get to the last one. So the last one we have is postorder. Postorder traversal prioritizes left before right and will visit the left child, the right child, and the parent in that order. So here is postorder. So it's going to prioritize left before right. It's going to be first one's here. 1, same as Inorder. Then we're going to go 2, same as Inorder. So first we go all the way down to the left child, and then we're going to prioritize the right child. So then we're going to go all the way down to the right, go meow, all the way here. 3, and then we're going to go here 4, and then also 5, and all the way back to 6. Okay, and that's post order. So let's kind of break it down a little bit more. So Inorder is sort of, we want to search the left half of the tree, then the root, and then the right half of the tree. So Inorder, so it's left child to root to right child. Okay? So Inorder, that's the purple one, right? We prioritize left child over here. And then we went to the root, and then we went to the right child, which is the 6. But then we go here, and we prioritize the left child again. So left child, root, right child. And then preorder is going to be prioritizing left before right, and it'll visit the parent, left child, and right child in that order. So it'll be parent to left child to right. So again, it was the green. I'm gonna use a highlighter this time. So parent is here, 1. Then here, this is left child, but it's also the parent. And then here, we hit 3. And then we go right. And again, this is technically a parent, so it's gonna be number 4. Left child, 5. Right child, 6. Okay? And then postorder is going to be the left child to the right child to the root, to the parent. Okay? Let me change root to parent so it's all the same language. And that's the only difference. So in order, left, parent, right, 1, 2, 3. Preorder is going to be parent, left, right. Postorder is going to be left, right, and then the parent last. Okay? Any questions about the conceptual idea of this? We're going as deep as possible, and we're prioritizing different IDs. We're either prioritizing the left, the right, the parent, or the right. Any questions so far? You probably learned about this in your discrete math class. I know I did in 220. If not, then let's start. All right. In order. And this is going to be actually kind of funny about how easy this is. So given the root of a binary tree, return the in-order traversal of its nodes values, and you want to actually output the numbers as sort of like an array. So we're going to have a result, call it res, and just empty array. All right? And then we're going to make a new function because it's going to be recursive. So def in order, we're going to have a root as our intake. If not root, so if the root is null, just return. That means it's just go back. And then we're going to run these in order. So in order, root.left, because we're prioritizing left. Then we're appending the root.value to our results, because it should technically be the left side. And then in order, root.right. And that's the definition of in order. So we prioritize the left, then we go to the root, and then we prioritize the right. So we just run it in order, root, and then return the result. And it works, easy peasy. So like we talked about again, I know this is going left, root, then right. And we're adding it to our list, so we would have an output over here. Okay? Just a fun fact, you can do these traversals as well iteratively. You would have to use, I think, a stack data structure, and you'd have to kind of do it yourself manually. We're not going to go over that over here because it's more of an advanced idea. For now, recursive is easy peasy. Okay? So we're going to do in order. And then here's the magic. Here's preorder. So I'm going to just copy and paste everything. And then I'm going to move this up 1. And that's it. So in preorder, we went for root first, then left, and then right. And that's preorder traversal. Great. So then postorder. Paste it again. and then just change the name. Post. And now I'm gonna ask you guys, what should we move in post order for this to be post order traversal? Where should we move this recipend? Does anyone know?
Last.
Yeah, last. It's literally that easy. You just move one thing around, and then you have pre-order, post-order, and in order. For some reason now, one time it was 20%, now it's 71%. Anyways, the idea is this is O of n, because we're going through all nodes for all of them. So big O of n. Any questions on pre-order, post-order, and in order? No questions? All right. Last one. So just to summarize, we've done a lot today. This is practically half of your CS 220 class, I feel like, and it's like a couple of weeks of your 313, and we just did it in 1 hour. So congrats if you made it this far. This is good. So we've gone over search in the binary search tree. We've inserted, which we know is at the leaves. Delete nodes in the binary search tree.